and all talking about some of the challenges, issues, and opportunities around water supply here in Whatcom County. We know that's an issue not only for the small fruit growers here, but we've also advertised this session for the broader community, because many of the topics you're going to hear about this morning are actually relevant to all kinds of water users here in Whatcom County. So I want to mention a couple of things before we get going and I introduce our first speaker. We are actually video recording all of these presentations, and so they're going to be available on the WSU Small Fruit Conference website. So for those of you that know people that weren't able to attend, they will actually be able to see all the presentations later on. And a number of logistical things, just for those of you that have never been here before. Restrooms are over in that far corner. There's also coffee over in that corner. We do have one break scheduled. So, head over there if you want anything to drink. I want to mention a couple of other things before we get going. And one of them is you're going to be receiving during this morning this blue sheet, which is our evaluation form. Rebecca Schlotterback with the PUD will be passing those out. And we're asking, even if you aren't able to stay for all of the sessions, all the talks this morning, please fill out what you can for it and put them into one of two boxes on either end here. We take those things very seriously. It helps us understand how well we did today in providing you information that we hope is useful and relevant to you, but we're also using them to help figure out what we want to talk about at next year's conference and maybe a number of other events throughout the course of the year. So please take a moment, even though it's front and back, and I know people don't always like it, looks like a lot, but there's a lot of things that are just simple check marks. So it's not as onerous as it looks. And with that, I'm going to pass it on. Oh, one more thing. I'm also part of the Whatcom Watershed Information Network. We do a number of things to try and provide information to the community on important water issues. This year, one of the things we did was we held a water photo contest. So there's a number of calendars available over there for 2017 if you want to pick them up. Photos that are celebrating the importance of water to our economy, to our environment, and to recreation. So you'll see photos from local photographers in Whatcom County celebrating all those different things. And so please feel free to grab one if you'd like. With that, I'm going to turn the presentation over to our first speaker, which is Nick Bond, and he is our state climatologist. And I asked him, and I want to say special thanks to Nick, because I asked him to be the first speaker today, which is pretty early to be driving up from Seattle. But he's going to talk about really the fundamental driver for all the issues and challenges that we've got here, which is how much water do we have, when does it occur, where does it occur, and what did it look like in the last bit of time, and what's the future look like? And so with that, I'm going to pass it over to Nick. Thanks, Nick.
Yeah, thank you, and it's a pleasure to be here, and it was no problem driving up here. I wake up early anyway. Sue asked me to talk about, about this recent climate event and to put it in kind of a historical context in the climate change. And so I thought it was appropriate to start off with this cartoon from slightly adapted from David Horsey when he was doing this for the Seattle PI. In the upper left corner, it might not be that visible, and then the date there is January 2053. And so, like good satire, how close to the truth is this? All right. With regards to our recent climate event, and we should consider that a short-term climate event, it really got its start in the ocean. A lot of my research has to do with how the climate variability and change affects the marine ecosystem. I couldn't help but notice in early 2014, it was getting really warm relative to normal. This a map shows temperatures, sea surface temperatures relative to normal, 2.5 degrees C. That's a big signal. I reached deep into my vocabulary to come up with a term for that, and boy, didn't that take off. So we won't say anything more about that. But it is just one of the things that has really kind of galvanized some of the climate science and some other things of people looking at forests, wildfires, the marine ecosystem. There's been a lot going on in the West the last few years. And so can we learn from what's been happening? So today, what I'm going to do is briefly summarize this event that we've been, I would say, enduring, and then putting that again into the context of both historical trends and what the climate models are suggesting that is what we're liable to see in the future. Just as kind of a little bit of an aside before I get started, I am your state climatologist. Many of you probably didn't realize you had a state climatologist. That's cool. But we're here to kind of help you, and we take calls from and requests from all sorts of folks, state agencies, private individuals, and that sort of thing. We're easy to find. If it's too big of a request, we'll tell you to buzz off or whatever, but don't hesitate to contact us. We're here for you, and we're interested in the issues that you guys are facing and the climate information that you need, because then we can provide just that much better service. All right, so it's been warm. Hey, no lie, right? Well, it's been record warmth. Here in the climate community in the West, we like to think in terms of water years. I assume many of the people in the room do also, starting in October and going through September. The regular calendar doesn't work as well. So yeah, it was very hot. This shows the temperature anomalies across the Pacific Northwest, with many places up 4 or 5 degrees Fahrenheit above normal. Then again, records. And one of the consequences, of course, was just a dismal snowpack coming out of the winter of 2014-15. This plot shows the percentages of the usual snow water equivalent, the amount of water in the snowpack bank on April 1st in various watersheds, and here in the Olympics especially, 3% of normal. Wow, never seen anything quite like that. So again, getting back to putting it in a historical context, this is kind of a complicated plot. It looks like somebody ate a bunch of Skittles and threw up or something, but what it is that each of these dots shows the temperatures and precipitation in individual winters, kind of color-coded, so the bluer they are, lighter blue, the further back in time, the redder, the closer in time. And so this shows on the vertical axis here how wet it was, and on the horizontal axis how warm it was. And here's the 2015, signifying the winter of 2014-15, just showing how what it was really unusual was in terms of temperature. Precipitation was very near normal. It was a snowpack drought, not a lack of precipitation drought that the state suffered. I'll just kind of skip that. There's I could go through for hours all the sort of things that happened. One thing that we were really struck by in the climate office was some of the heat that occurred in June of 2015. And I'd be very interested from you folks, maybe have some comments and questions afterwards. Did this make a difference to you? I would think that a raspberry might not really like that so much, because obviously our usual summer weather here really starts getting consistently warm more in the middle of July or so. And the really extreme heat was in Eastern Washington, but it was in the 90s for multiple days in Western Washington too, and that's highly unusual. It wasn't just the weather that was weird. Our areas, or the ocean, it was the area streams. This is this picture taken at the mouth of the White Salmon River in the gorge, a tributary of the Columbia. That's those are sockeye salmon. This one's not getting to its spawning grounds. This one's got a fungus that it's pretty much doomed. A huge run came through Bonneville Dam. Very few of those fish actually made it up to their spawning grounds, and the water was just too warm for the salmon. I have an example here from our, in the backyard here of the Nooksack River. And this shows, the blue trace shows the temperature from January of 2015 through, the end of summer of 2015, and shows the temperatures. And note this rise into the 70-degree plus in kind of late June, early July. These gold dots show the average for that time of year. And what happened was it warmed up a lot more than usual and much earlier than usual. And that can be directly attributed to the lack of snowpack. There was plenty of water in the winter here. This is Streamflow, again with the blue being 15, the average showing the gold dots. And so usually there's a fair amount of Streamflow in the winter, of course, and it hangs on due to the snow melt into June and then goes downhill. Well, in 2015, it went downhill so fast, that's why it warmed up so much. And so there's some real implications there. There's ecological issues having to do with the water temperatures here, and eventually that may play a role in how we use our water. All right, so long-term trends. What I plotted here, or I've just lifted a plot from a fairly recent paper showing based on actual measurements, no models or anything, actual station measurements for the period 1920 to 2012, the temperature trends for the different seasons, winter, spring, whoops, let's go back here, summer and fall, and both the kind of afternoon temperatures and minimum temperatures, nighttime temperatures. And so you can see that the redder the dot, the higher the rate of warming. There's a few places that have actually cooled, but I would say that the vast majority of the stations have warmed over that period. And again, the redder color is the greater rate of warming. Some interesting seasonal differences, and in particular, it seems like the minimum temperatures are going up a little faster than the maximum temperatures. I'm gonna focus on that a little bit. If we look at, for example, for the Washington state as a whole, kind of a different perspective, and here June, August, if you just look at the average temperatures, there's a noticeable upward trend. Here's 2015. For reasons escape me right now, I didn't put 2016 on it, but it was down from 2015. But there are a lot of year-to-year variability. On the other hand, if you look at the minimum temperatures, and I'm going to toggle back to that one, an upward trend, but a lot of noise there. If you look at the minimum temperatures, and here I'm just actually looking at the Puget Sound Climate Division, which this kind of the lowlands, Skagit and Whatcom County lowlands are part of, that a much more systematic upward trend. And there's 2015, what is sensitive here? 2015 setting a record. We're down a little cooler in 2016, but that is concerning. And so that, and then this record goes back a long ways, and it's good, solid data. That, and we know why, in part, that is happening. It's getting a little more humid around here. Now, have you guys noticed that in the summer nights, or just, it's nothing like Mississippi or some awful place like that, but it's just a little stickier than it used to be. And the nighttime temperatures just aren't dropping down quite as much as they used to. And here you can see that is associated with a slight but noticeable uptick in the humidity around here. And no signs of that. Of course, 2014 was the record here. And as a kind of an aside, this blip back here was last time the water off our coast was really warm, when the kind of the first blob or so. All right, I'm going to spend a little time here focusing more on kind of this neck of the woods. And so I just put up this map for a couple of places I'm going to talk about is snow at Beaver Pass, some stream flows at Arlington on the Stillaguamish, at the Sauk near it where it meets up with the Skagit. Let's see what else. Oh, also some flows on the Skagit itself. And so let's start right off with the Beaver Pass snow water equivalent. on April 1st, kind of the end of the winter season. This is kind of a medium elevation. I think it's 3,800 feet or something. And so it's pretty sensitive to the temperatures in winter. And you can see back to the 40s. Again, lots of year-to-year variations, but basically a downward trend with the 2015 being the, you know, the absolute worst there in the record. On the Stille, here, the Streamflow records, again, going back quite a number of decades. Here, what is plotted is the peak flow each season. And that's something from, you know, design characteristics and something we have to keep track of, kind of the maximum flood. The Stillaguamish is a rain-dominant river, and so it reflects that the really extreme rain events are becoming that much more extreme. You know, plenty of year-to-year variations. You get a somewhat different perspective on the Sauk, which is much more snow-dominated in its upper part of the watershed there. It's not far from the Stillaguamish, but a much different kind of seasonal cycle in its flows. And there, yeah, there may be an upward trend, but it's not statistically significant. And there's, you know, still plenty of year-to-year variations. You can see a factor of 6 between some years, the strength of the floods, the peak flood versus other years. All right. One thing that is changing though on the Sauk and for the area of rivers in general is that time of peak flow. And so on the, I'll try to do this without advancing the slide here. This is how late in the season you have your big flow, your max flow on the river. And so these peaks around here are kind of with winter rainstorms. And these peaks here are more like with spring snowmelt. And so you can see that the peak flows on the Sauk used to be mostly, not always, but mostly associated with snowmelt. More and more, they're having to do with the kind of flooding events in the wintertime. In terms of another thing, I like to use the Sauk River because it's unregulated, and so it shows what would be happening if we weren't kind of, you know, messing with it. We mess with the Skagit plenty. This shows the lowest 7-day flows of each year, and they're a very noisy signal there. Maybe there's you know, some in the recent decades, a little bit more likely to get really low flows, but I wouldn't say that there's, we're seeing much in the data yet of that sort. And so with that, that's kind of a whirlwind review of the, you know, sort of the conditions we've been seeing around here. And so in the last part of the talk, I'd like to talk more about what the climate models and those climate models, some of the results that I'll show when they're run through hydrological models, what they're indicating for the amount of stream flow and the timing and so forth. So first of all, the models show that it's warming. Okay, I'll give anybody in this room a nickel if they can tell me how much warmer than normal was it in the 2014-15 water year. I showed that slide. Anybody want to hazard a guess? Say again. It was a little bit more than that. It was something like 3 to 4 or so. And actually, what the models are showing, though, in this A1B, these red boxes are probably more indicative of how it's going. But the models are showing that temperatures in the 2040s that are going to be comparable or even greater on average than our warm event here in the last couple of years. And so this is kind of scary stuff. On from a kind of more well, spatial distribution, you can tell plots that I made, by the way, because they're kind of ugly looking and plain. So this is one of my specials. But anyway, what I'm indicating here is just a bunch of models, all averaged together, what they're showing for the change in temperature from going from the end of the 20th century into the 21st century into the kind of middle of this 21st century. Oh, okay. Oh. Okay, cool. Yeah, that'll help. Yeah, and so what this is showing is for the kind of rain, the wet season, I just picked November through January, where it's predicted to warm up something like 2.5 degrees Celsius, something like 4 degrees plus Fahrenheit, and with greater warming on the east side of the state than in the coastal region. Anybody want to hazard a guess? Why is there less warming along the coast? Shout it out. Somebody's got it. Bingo. Okay. Yeah, if I had a cigar, you'd get it. But yeah, okay. Yeah. High stakes here. Yeah, and so the same thing happens in summer with, again, the forecasts are warming, a little bit more warming in summer than in the wintertime, with greater warming on the east side of the Cascades with the less moderating influence of the ocean, which has a lot of thermal inertia and is just warming up slower. All right, precipitation, this is the big one, okay? Again, divided by season, and here looking at different sort of periods that this is on a percentage basis, and so what it's showing for the most part is wetter winters and slightly drier summers. The little dots here show the results from individual models, and it shows like there's not a overwhelming consensus there. Some of the models are showing a little drier, more are showing a little wetter, and so there's some uncertainty, but in general, especially as you get later into the 21st century, wetter winters and drier summers. Again, if we look at this is percentage, in more absolute terms, and again, looking seasonally and spatially, that here wetter, especially on the west side of the state, and but a little bit wetter east of the Cascades, and in the summer, drier on the bigger change on the west side than on the east side. These actually, you might be hard to read these numbers, but this is something like 8 to 10 millimeters less, not much less in summer compared to the increases of the tens of millimeters in the winter time. And so we're gonna, it looks like we're gonna have even more of a Mediterranean climate than we have right now. People don't necessarily equate this with, you know, Nice or something like that, but technically we do have a Mediterranean climate. This is kind of a, well, bear with me here. One of the things that I'm kind of interested in is in part because of what's happened in California and the multi-year drought there, is there any indication that droughts, which right now in Washington State tend to be 1 year toward events, you have a dry year and then next year, who knows what's going to happen. Is there any tendency for multi-year droughts in the future or multi-year wet periods? And the answer is, again, looking into those models, is that where this red blotch is that that's where there's going to be less persistence from year to year. So if anything, at least in Washington State, less of a tendency for multi-year dry and warm periods. That's probably good news. Yeah, I didn't show the whole West here, but there are parts like in California where it looks like there's going to be more multi-year wet and dry periods, and that's not good for them. All right, here's another complicated plot for you to, you know, wake up to or something. Again, getting back to this past winter here, in terms of how different it was in temperature along this vertical axis versus how different it was from precipitation along this axis, and comparing it with what the models are showing for our future winters here in the middle of this century. Okay, and so in some ways, what the models are showing is some models not that much warming, but the others are showing that the that winter is going to be typical of the future winters. But I want to point out that this, this plot, which from a paper recently published, was using a scenario in which greenhouse gas concentrations are relatively low. And with a more, we're following a path with higher concentrations, and so chances are these temperatures are going to be actually warmer. All that what that means is, of course, a large drop in the snowpack in the mountains because of climate change. This is some model results that have been done that have shown that compared to, and this is at Stampede Pass in the Central Cascades, showing a big decline by the end of the century. And what I think is more conceivably more important again is the type of streams we're going to have. And for many purposes, they've been divided into 3 types. And here there's some kind of local examples here. There's the rain-dominated ones, the Stillaguamish, the Samish, that just, their watersheds mostly receive rain, big flows in winter, not much in summer. There's the ones that get both rain and snow, kind of like the Snohomish, that have this black trace here shows their flow over the course of the water year, where they have a lot of flow in winter with the rains, and then snow melt, another peak. And so those are kind of mixed or transition or transient rivers. And then there's ones like the Sauk, and some of the tributaries, the Skagit, that are snow dominated, that have big flows in winter, but their main flow is in the summer with the snow melt. So what we're seeing is with, based on the change in the climate, is a transition of a lot of these mixed rivers from this double peak to a single peak, just more rain than snow in the mountains, in the elevations of the watershed, and for the snow dominant rivers to go from that to one of these kind of mixed types. And that's another set there, more, the Chehalis is an example of the Yakima, which is now a mixed, probably go to a rain dominant. The Columbia, at least, looks like it's going to stay snow dominant. A lot of its water comes out of the high terrain in Canada, and so it, that looks better in the future. To give you kind of a more of a spatial perspective here, this map shows the 3 different kinds of river basins, with the rain ones being the green. These mixed ones are the double peak streamflows, the reds, and the snow dominant in the blues. This is the present situation. And you can see here with 2 different sort of scenarios for the climate as a whole, as we go out in time, 2020s, 2040s, the number of watersheds that are of the blue type shrink, and the number of kind of rain dominant watersheds grows. And so this is going to have, again, a real implication for water supply. All right, what about the Skagit itself? Another complicated graph. I guess I'm specializing in those this morning, you know. But what I'm showing here is on the top 2 boxes here, or plots, are what would happen if there weren't any dams in the Skagit. This is based on models, just knowing what the temperatures and precip and so forth would be, and how much runoff there would be run through a hydrological model. And so it's kind of it's an exercise, but it's a way that we have to do that because we're using the same kind of data to from the climate models. But anyway, this blue trace is what the Skagit would do. It's stream flow over time, you know, kind of through the water year, if there weren't any dams in the way, with a bit of a peak in wintertime, and then the snowmelt peak. This is what the models are indicating with kind of a range for the 2040s and 2080s. Again, a little bit more of a wintertime peak if there weren't any dams on the place, and especially in the 2080s. But last I looked, there are some dams there, and they do regulate the Skagit River. And so using the present flood control rules, they went through the same exercise. This is the actual historical sort of kind of stream flows on the Skagit, and using those rules and what the models are showing it. I think this is actually pretty good news, at least for the next couple of decades, in that it doesn't look like the flows on the Skagit will have to be that much impacted by climate change, at least with our ability to regulate them. As we get into the 2080s, that's going to get more difficult, where there's just going to be so much water coming out, and they're going to have to leave room for flood control, that it's water that's relied upon in the summertime just isn't probably going to be there. All right. In terms of the actual peak flows, how bad the floods are going to be, and presumably that's an issue for some of you guys. If the Skagit's running really high, then you know, in terms of your groundwater, even flooding fields and so forth. Again, there's, I think, some good news here is that, first of all, these X's show for different times the peak flows in the historical record, with along the horizontal axis here, what time during the year those peak flows are, and the vertical one is how extreme that is. And so the X's are the actual observations. And here in the 2040s, given modeled amounts of precipitation and temperature and how much is running down into the watershed, you're kind of making some estimates of the peak floods, and they don't look to be that much greater in magnitude. This is good news. There's much more of the floods are going to be early in the water year rather than late. And that's especially the case in the 2080s. But even if you get into when you get into the 2080s, it's not like the max flows in the Skagit are expected to be double what they are now, or any disaster like that. So good news. Yeah, I'm going to skip this one. It's too complicated just in the interest of time, but basically I have tried to do the same thing for the low flows, and there's some indication that the lowest low flows are going to be a bit lower, but again, with regulation, it doesn't look like a disaster. Some of the modeling that's been done has actually been on soil moisture. And again, I'm not sure if this is an issue for you guys, but where these red colors are is showing where it's kind of a percentile basis, and so where the soils are drying out. And this is in the 1 July in the 2020s, 2040s, 2080s, and again, different kind of climate scenarios. Probably this left column is most relevant, and it shows especially the high Cascades, but most of the west side is going to be drying out, and this is of course assuming not accounting for irrigation and so forth. As kind of an aside, it's actually soil moistures are expected to go up in eastern Washington. And what? How's that? Well, they're already dry, and with the additional precipitation in the high terrain, actually in this modeling study, it shows a little bit more moisture there, but still, you know, it's a percentage basis, so, and a difference, and so it's still pretty dry, as shown in this upper right plot. Okay, I talked about the temperatures on the Nooksack and in the Columbia Basin in 2015. The stream temperature is really bad for fish. That's gonna end up being a constraint. There are some endangered and threatened species, and there's some rules to keep conditions there ecologically in okay shape. Some work has been done about looking at the relationship between the climate, the weather, and stream temperatures, and in most places there's a pretty good correspondence between just how warm it is in the summer and how hot the streams get. And so this map here shows the temperatures, the colors are the temperatures in August, And these little dots are the stream temperatures here with this code at the bottom. Various places where we have measurements. And there's not a perfect correspondence, but basically where there's the cooler weather, there's cooler streams. So we can use the relationships on those individual streams based on the historical data and forecasts of stream flow and air temperatures and so forth, and get an idea of what those stream temperatures are going to be like in the future. And that's pretty bad news, in that a lot more of those streams are going to get into those temperatures that are harmful or even fatal to salmonids and trout, and things like bull trout and some of these other stocks. They're doing everything they can to maintain them, and there's going to be water that won't be available for irrigation to maintain the ecological habitat in the streams. One last thing I want to talk about is the Columbia. And again, I mentioned before that the upper part of the watershed is in Canada. Still a lot of snow going to be expected up there for the foreseeable future. A lot of the water in the summertime comes out of Canada for the Columbia. And so a colleague of mine has done some modeling of that, which is, again, if there weren't any dams, and that's, a great fiction for the Columbia, but the amount of water versus time of year, these are months along the horizontal axis here, is if there weren't any dams coming out at the Dalles, is based on our historical climate, has that kind of trace, with much of the water in the summertime coming out of Canada. Well, it turns out that there's going to be, if you didn't have any dams, there'd be less water coming out in summer, but more in the wintertime, a little bit more rain than snow in the higher elevations, and the total amount of water coming out of the Columbia is expected to increase. And so if you're depending on water for the Columbia Basin project, you're pretty good shape for the foreseeable future. Again, because that's so highly regulated. All right, so just to summarize, I hope I've convinced you that we've had a record event, and from as a state climatologist, well, it's good for job security, let's say. That hopefully you folks haven't suffered too much, but it's been a wake-up call, and hopefully we can learn from it. There's a very strong indication that of warmer temperatures in the future, but also probably wetter winters, and the more recent model results are confirming that. Maybe there's less certainty about this, slightly drier summers. And so what that means is, just on most streams, more flow in the wintertime, less in the summer. And I raised this question, is it going to be water supply or water quality that really constrains us in the future? During 2015, well, first of all, in Washington State, I understand there's something like 10,000 different water supply systems. Most of them really tiny. And a lot of them on a small stream or shallow well, had problems with water quality in 2015. And so water quality, just both for a human health perspective and for keeping our streams as healthy as possible, that may be a big issue. And so again, I'd like to close with another horsey cartoon. And then finally, here, I think these slides are going to be available for those who want to look at a little bit more. Here are some references, some reports put together by Ecology, Bureau, Reclamation. They're not, well, a mix of kind of technical and very accessible. And so I'd encourage you to check those out. So thank you.
Thank you, Nick. So we have time for just a few questions here at the end before our next session starts. And there's some mics floating around, so raise your hand and someone will hand you a mic. Don't ask your question without the mic because we're trying to record this.
So, okay, so you didn't mention glaciers or glacier melt. And so like the Nooksack or the river we get is partly snow, partly glacier melt. And as they recede, and they are receding, I assume,
Yes.
there's going to be more siltation in the river, so flatten out a little bit. Again, increases the warming and so forth. Have there been any studies or calculations on how long the glaciers will last? And
Boy, that's a great question, and I'm afraid I'm mostly ignorant of those results. I know some folks have been doing some work on that. At least the bigger glaciers make an attempt to try to handle that. But I'm not sure that that is characterized so well now in our current models. And so, and especially the impacts of the silt and how that's going to change the river channels. Boy, that's, my guess would be that's an open question.
And I am not the expert on that either, but I know some work has been done here locally on that. And maybe one of our other speakers can at least give some reference to that. Steve, are you able to mention that later? So bring that question up again when Steve does his talk.
I'm forgetting the fellow's name at Western. He's done a study on that, and that was he did a great lead into my question, and that is with the increased temperatures, are we seeing a reduced signal from increased temperatures to summer low flows because we have increased melt of the glaciers, and how much longer will that persist?
Yeah. My understanding, and maybe somebody can correct me if I'm wrong, is that the glacier contribution is relatively minimal. Yeah, you know, it certainly helps at the very lowest flow times of the year, but for most of the, there are some exceptions in the Olympics and so forth, but we're not going to be able to count on our glaciers to bail us out to any great extent. And
a question on the modeling in Skagit and in the Columbia. Do you know if the model took into consideration, I mean, high stream flow or high runoff during certain times of the year, but the ability for the operators of the dam to release that flow, not only for flood mitigation, but the whole impact of high gas volume in the water and how it would impact fish? I mean, I know they're constrained.
Wow.
Significantly.
Yeah, so the question has to do with, there are rules having to do with during fish migrations and avoiding too much spill, and the fish get the bends and so forth. And as far as I know, that hasn't been incorporated. At least some of the results I showed for the Skagit did include consideration of current flood control rules. Most of the stuff on the Columbia has just been this fiction that we don't have any dams in the way.
One more quick question. Anybody?
Oh, over there.
You talked about the oceans warming up early and kind of being the cause of this. What caused that?
Well, yeah, and it's a complicated story to a certain extent. The oceans helped make the winter, because they were warm, they helped make the winter 14, 15 that much warmer. It was probably a secondary contribution, but it was kind of unusual weather patterns in that winter of 13, 14 that started the blob in the first place. And we think that a lot of that can be linked to weird stuff that was going on in the far western tropical Pacific. It's kind of like El Nino, but with its roots further west. And so it was unusual weather patterns in 13, 14 that kind of kicked off the whole event. But for the most part, we can't blame the ocean for how hot it is. It's been, anyway. So I think I should step off, and thank you.
Yeah, and Nick, are you going to stick around during the break?
Yes.
Okay, so for those of you that didn't get a chance to answer your question or ask your question, he will be around. I'd like to introduce our next speaker. It's Doug.